everyone, thank you so much for clicking onto the video. Today we're going to be learning about free energy, and here are our learning objectives. So the first is to explain that the feasibility of a process depends upon the entropy change and temperature in the system and the enthalpy change of the system. We're then going to explain and related calculations of the free energy change, and that a process is feasible when this delta G has a negative value. And then we're going to look at the limitations of predictions made by delta G about feasibility in terms of kinetics. Now I'm going to introduce Gibbs free energy change. So Gibbs free energy combines enthalpy change and entropy change. So this is an equation we have for Gibbs free energy. So delta G is the change in Gibbs free energy. The delta H is enthalpy change, as we've already learnt. And then the T stands for temperature. And then the delta S is the entropy change. Now we know that a decrease in enthalpy, so a negative delta H, so an exothermic reaction, is more favourable in a reaction, and an increase in entropy change, so a positive delta S, is more favourable in a reaction. So overall, if delta G is less than or equal to 0, then the reaction is feasible, and feasible just means that the reaction can take place. Sometimes the word spontaneous is used, which means thermodynamically possible, which is quite similar to feasible, but it is better to use the word feasible. And we can see this because if we have a look further at the equation, delta G equals delta H minus T delta S, it's favourable for delta H to be negative. So if this is negative, and then we're minusing the delta S, which is favourable when it's positive, that means that the delta G is feasible when the reaction is less than or equal to 0. So when delta G is less than or equal to 0, then the reaction is feasible. And that's because the enthalpy change is favourable and the entropy change is also favourable, because if we have two negative figures, then that will ultimately be negative. And it's very important to also note that temperature is included in this formula, and so that means that the feasibility of reactions actually depends on the temperature as well. So we can make things feasible when they're not feasible by altering the temperature. However, one thing to note is that even though a reaction may be feasible, the activation may be too high, the activation energy, may be too high for the reaction to actually take place. So here is a nice table to summarize how Gibbs free energy changes with temperature. So if we have a look at the first example, if we have a negative enthalpy change and a positive entropy change, then the delta G will always be negative, so it's feasible at all temperatures. And so we can see this because if we've got delta G equals delta H minus T delta S, if we have this as a negative, and then we have minus, and then the delta S is positive, that means that this will always give a negative value, no matter what the temperature is, because the temperature can never go below 0. It'll always be positive. And then for the second example, we have a negative delta H and a negative delta S. So we've got T and then a negative delta S. And this means that if we lower the temperature, then the delta G will be negative. But if we have a higher temperature, then the delta G will be positive. And we can see that because what we have right now is that we have a negative plus T positive. And so if this T positive is equal to this minus delta H, then what we have is that this delta G is equal to 0. And this is the tipping point, whether the reaction is feasible or not feasible. So which means that when we have a very, very high temperature, that means that this will exceed the negative, so the negative delta H. And what will happen is that we'll have a negative plus a very, very big positive. So then delta G will be bigger than 0, making the reaction unfeasible. Whereas if the temperature is very, very low, then we'll have a negative plus a very small positive. So it still won't, the delta G still won't exceed 0. So then we have delta G is smaller than 0, making the reaction feasible. And we can go along and apply the same kind of logic to the other two examples we have. So we have for a positive delta H and a positive delta S. So if we lower the temperature, then the delta G will be positive, and if we raise the temperature, then the delta G will be negative. And for the last one, we have a positive delta H and a negative delta S, and the delta G will always be positive. And I'm going to explain this by saying if we have, so writing out the equation again, we have delta G equals delta H minus T delta S. So if this is positive and if this is negative, because the temperature can only be positive, it can't go below 0 Kelvin, that means that this will always be positive because we've got two minuses here which equal a plus. So we'll always have that delta G is bigger than 0, so it will never be feasible at any temperature we use. Now we're going to look at some graphs of Gibbs free energy change over temperature. So on the left we have the equation of delta G equals delta H minus T delta S. Now we know we can plot straight line graphs by using the equation y equals mx plus c. This is the equation for a straight line, so the general equation. And so if we fit our delta G equation into a y equals mx plus c format, then we can plot straight line graphs. And so what we do is we make the delta G y, and then we have mx here, and then we have a plus c. So we have that y is the delta G, x is our t, m is our minus delta s, and c is our delta h. So if we plot a graph of delta G over t, then we get a graph of y over x. And y stands for the y value, x is the x value, m is the gradient of the graph, of the line graph, and c is the y-intercept, so where this line crosses the y value. And so from this, we can see that if we plot a straight line graph, then we can find the enthalpy change by seeing where it crosses the y-axis, and we can find the entropy change, the delta S, by doing m equals delta y over the delta x, and this would be negative. So if we worked out the gradient of the line and negated it, then that would give us the entropy change value. And so if we look at the graphs on the right, on the first graph, we have an endothermic graph. This is where the delta H is positive and the delta S is also positive, because we see that the gradient of the line is negative, but that equals the negative of the delta S, so the delta S must be positive. And so we see that on the graph, from this point to this point, the reaction is not feasible. And this is because delta G is bigger than 0. So the reaction is not feasible. However, at this point, the reaction becomes feasible because this is where delta G is equal to 0. And then we have that this bit of the line graph is where delta G is bigger than, is smaller than or equal to 0. So then the reaction becomes feasible. So we can actually read off the temperatures where this reaction will be feasible using these kinds of graphs. And then at the, looking at the bottom graph, this is an exothermic graph, and we can see that because we have a negative delta H, because where it will intercept the y-axis will be somewhere down here, so it'll be negative. And then the delta S, the entropy change, will be negative because the gradient of it is positive, but the gradient is the negative of the delta S. And so again, we can see where it will be feasible and where it will not be feasible. So from this point to this point, this is where delta G is smaller than or equal to 0, so the reaction will be feasible. And then from this point to this point, we have that delta G is bigger than 0, and so the reaction is not feasible. If we do have a graph that looks kind of like this, so we've got the temperature on the x-axis and delta G here. If it looks something like this, and it looks as though it will never cross this x-axis where this delta G is equal to 0, then that means that this reaction will never be feasible. So this is never feasible. And this is because delta G is always bigger than 0. So what we do first is we write out the equation. So we have delta G equals delta H minus T delta S. And so delta G we're trying to find, so that equals delta H, which is minus 185, then minus T, which we always need in Kelvin. So they've nicely given it to us in Kelvin. So we use minus 298, and then that will be multiplied by the entropy change. Now the entropy change, you have to realize, is measured in joules per Kelvin per mole, and delta H is measured in kilojoules per mole. So we need to convert the delta S always. So we convert this delta S to kilojoules per mole per Kelvin. And you can either do that or convert the delta H, it's up to you, but they both have to have the same units. And so then we have to multiply by times 10 to the minus 3 or divide by 1,000. And then that gives us a delta G value of minus 191 kilojoules per mole. And then for B, is this reaction feasible at this temperature? We know that when delta G is smaller than or equal to 0, then that means that the reaction is feasible. And so this means that this reaction is feasible at room temperature. So room temperature is 298 Kelvin, and we've worked out the delta G for this temperature, and it's minus 191, and that's smaller than or equal to 0. So then that means that the reaction is feasible. And then for C, explain why this reaction may not occur at room temperature. The main reason is that the activation energy required for this reaction could be very, very high, and so this is why it could maybe not occur, even though the reaction is very feasible. So the activation energy of the reaction is very high.